We're having like just a few students, but I hope you will get the same information as we did before. So what did we learn in last class? Do you remember? I put on here actually. Right. So the maximum flow model. So before that, actually, we did we learned the assignment model, and the shortest path and the minimum spanning tree model. So basically, for the net flow models, we learned this 6 models. And the last Tuesday, we learned the first 2 transportation and the transshipment model. Then last Thursday, we learned the last 4 models. So for last 4 models, for the assignment model, what is the critical step? Do you remember when you formulate the problem as the linear programming model? What is the critical step? So do you still remember the example? You have 3 workers, 3 jobs. So what is the critical step? For each, you can think of this as origin or supply node. What is the number of units for each supply node? Just 1, okay? Because each worker can only work on 1 job. How about the demand destination node? Just 1 unit, right? So basically, 1 worker can only work on 1 job. Therefore, in the network flow model, you know for each supply node, they only have 1 unit of flow. And for the destination node, they only have 1 unit of the demand. That's the critical step. Then you follow the same steps as the transportation model, right? You can formulate the problem as the linear programming model. And you use the Excel solver to solve it, you can get the solution, right? And for each worker, the inflow minus outflow equal to net flow, since inflow is equal to what? No, inflow minus outflow equal to net flow. So inflow is equal to any inflow? For the supply node, for the worker?
1.
Inflow? 0. They're not getting anything. They only send 1 unit flow, right, to the destination node. Outflow is equal to 1, and the net flow is equal to 1. Okay? Right?
Net flow?
Right. Net flow is just a minus 1, right? Okay. So for the maximum flow model, what is the critical step? Do you remember? So exactly. So you have to add a dummy arc. By the way, what is maximal flow model using for? You want to compute what? The maximum flow from
the amount of units you can go from the origin to the destination.
Right. So amount of units going through from 1 point to another point. So you can think of that one is origin, the other is destination. However, this is different from what we talk about the origin destination in the other 3 model because you are adding the dummy arc. Therefore, all the nodes are what? What kind of nodes? So we have 3 kind of nodes, right? Origin node, the destination node, and the transshipment node. So in the maximum flow model, all the nodes are actually transshipment mode. In other words, net flow is always equal to 0 because you're adding that dummy arc. Okay? And in the Excel solver, do you remember the 2 tables? I said if you want to choose the whole table as the decision variable, what cost you need to put on the fictitious arcs? Means the invalid arcs. In the network in the graphical network, actually the arc doesn't exist, then you should put a higher cost or lower cost. Why?
Because you want to like maximize to make sure it doesn't see that as a like route to take.
Right, right, exactly. So you should add a large cost, right? Such that Excel solver give you a solution which do not give any units on that artificial invalid arc. Okay. About the shortest path. So the shortest path model is used for what? Finding the shortest distance or time traveling from one node, right, to the other node. So means you can also think of one as the original node, the other is destination node. So like when I come to school, my origin, for example, is home. Destination is here, the student building, and which path gives me the shortest time, right? When I drive. So you can use the linear programming model, and again, when you want to use the whole table as the decision variable in the Excel solver, what do you need to do for the non-valid arcs, the artificial arcs?
Blank.
Say that again.
Blank.
Blank. So what does blank mean? Zero. So what is zero actually? Zero for what? The capacity, right? So each arc has a capacity. So for non-valid, those artificial arc, you just leave them as a blank, or you put a zero because the Excel solver regard the blank as the zero. So the Excel solver will not give any positive value on that arc, okay? Because you are minimizing. And you have the x less than equal to capacity. Capacity is equal to 0, so x is equal to 0. So you do not need to choose the decision variable one by one in the Excel solver. Okay? About the minimal spanning tree model. What is this model for? Do you remember? Do you remember the water pipe for different houses?
All the nodes are
Also
connected.
short.
Right. All the nodes should be connected. Do you use Excel solver to solve it? No. How do you do it?
Find the lowest value and just scroll down. Precision is a new point. Find the lowest value from each this node, essentially. Lowest value.
Right. Very good. So basically, you have a standard solution procedure. You follow that procedure. You can start from any node, then find out the arc which has the lowest value, right? But if you have ties, what do you do? So several arcs have the same low value. What do you do? Do you remember? Right, choose anyone, arbitrary. And so it's possible the final network, the minimum spanning tree may be different, but the total distance will be the same. Okay? Any questions from last class? No? Then we are moving to the integer programming model. So far, we only talk about the linear programming model, and we said like the table, you can have 1.5 table, but in reality, is that true? Say the furniture company can make a 1.5 table or 20.5 chairs. No, right? So what is the natural way to make it an integer solution? You round it up or round it down, right? Looks like it's easy, it's natural, and the linear programming model is easy to solve. All the solver will give you the solution in short time. However, let's look at one example. If that way is the rounding up or rounding down of the solution would give you a good one. So this is what I'm talking about. If you relax the basic assumption fractional value, that's for linear programming, then for integer programming, you would think rounding off the LP solution. However, the rounding solution typically will not give you the optimal solution. And the IP solutions are usually not at corner points. So let's look at this example. So here is the summary of the problem description. The Harrison Electric Company has two products. Has the requirement of wiring hours, assembly hours, and a profit. So how many decision variables do we have? 2. And how many constraints? What are they? Wiring time, assembling time, then non-negativity constraints. Yes, very good. So I use L to denote the number of lamps, F to denote the number of fans. Yeah. Okay, number of the ceiling fans. Actually, these should be integer values. So your objective function is to maximize your profit and subject to those 3 constraints. But now you have to add this constraint as well. Both decision variables have to be integer. I'm not allowing like 1.5 or like 2.5 lamps. So comparing to the linear programming model, I have extra constraints, saying those 2 decision variables are integers. Okay? Clear? So that's the only difference. So if we use the graphical method to solve this problem, we can draw the constraints line, right? And this is for 2L plus 3F less than or equal to 12. Is the lower than this line or above this line is your feasible region? Lower, because it's less than. Similarly, for the other constraint line, that is 6L plus 5F less than or equal to 30, should be lower or up above that line. Should be lower, right? Below the line. So this is your feasible region. And then now I want an integer solution. So the whole red area is not my real feasible region. I need to find out those integer points. So look at the points with this plus symbol. These are your your candidate solution. Okay? So the optimal solution for the linear programming model, that is this one, right? So L equal to 3.75, F equal to 1.50, and the profit is 3,300. However, it is not my integer solution. So a natural way is for this 3.75, you would round up. You would think you want 4 laps, right? So this, and F equal to 2, so 1.50, you round up, then F equal to 0.2. So this rounded off solution, is this solution feasible?
No.
Why?
It's not in that.
Feasible region, right. Actually, this one, it's not the feasible solution. Means this solution doesn't satisfy these 2 constraints. So the round off solution is not a good way, okay? And the nearest feasible rounded off IP solution is L equal to 4, F equal to 1, right? This one. This is, looks like the nearest feasible rounded off IP solution. So then let's look at all the integer solutions. So we list, oh gosh, I want to give you the list. Something wrong with my, okay, here it is. So look at all the integer solutions, the feasible solutions. Here, this 4, 1 is the nearest feasible rounded off solution, right? However, this is not optimal. So the optimal IP solution is 3 lamps, 2 fans. So basically here, I'm enumerating all of the candidate feasible integer solutions and calculate the profit. And look among all this list, I found out this profit is the highest. So 3, L equal to 3 and F equal to 2 actually is the optimal IP solution. So this 4, 1 is actually your nearest feasible rounded off solution. So what does this example indicate? Should we just solve it as a linear programming model, then find out the nearest round-off solution? No. Yeah, but however, if you enumerate all the possible feasible integer solutions, then find out the profit, it's not sophisticated enough, right? Without taking this class, it's okay. But after taking this advanced class, you shouldn't do that. We should develop the integer model. So we know how to develop the integer model. Basically, for the linear program model, you add another constraint saying all the variables have to be integers, right? This is integer program model. That's the only difference. But then when you use Excel to solve it, how can we do it? So again, we can add this constraint. So basically, I will show you later about this range. Basically, this is the decision variables. I'm adding this solution must be integer. So I'm adding another constraint. And here the same, make the unconstrained variables non-negative and still use the simplex LP method. So all the others are the same. The only difference here, when you add the constraint, you need to add this. The decision variable must be integer. That's the only difference, okay? No. So, yeah, I want to show you this. So here, we know how to implement the model for the linear programming model. So this is exactly the same as the linear programming model, right? So you put the two decision variables. This is the objective coefficient, and then about the two constraints, because the real constraints is the two real constraints. And then, so as I explained here, this is the additional constraint, adding this B5. So this the cells highlighted in yellow, B5, C5 equal to integer. That's the only difference. Are we good? Yes? Okay. So I will talk about the binary variables. So integers can be like 0, 1, 2, etc. But for the binary variable means the variable can either be just a 0 or 1. This is what we call the binary variable. And it can be used on the selection problems, set covering problems, also later on about the facility selection problem. So let's look at this example. So how many decision variables would you define for this problem? Seven. What are they? The choices, right? So your decision variable would be this 7 different kinds of investment. And here I define the T, so basically I'm using the initial ladder of each investment, okay? So here, the laser point is not working correctly, okay? So the Texas oil, if the Texas oil is included in the portfolio, that's equal to 1, otherwise equal to 0. So you define the other 6 decision variables as well, and using the similar method. So if the investment is included, you would say this decision variable is equal to 1. And then your objective is to maximize your return of investment, right? So how do you get the return of investment? So this is from the problem description from the table. You have this expected annual return, right? So here, for each of them, this is you have this expected annual return. So for each of this coefficient, that's the expected return, time your decision variable. This is will be your return of investment. Then what are the constraints we should have? You have the upper limit of the investment, right? So for each of them here, it has this cost. So that is cost. So again, for each option, you time the decision variable, add them up, should be less than equal to your upper limit of the investment. So that is the first constraint. But why do we need the second constraint? Because of what? Right. Here, at least 2 Texas companies must be in the portfolio. But why I'm only choosing T plus H plus L? Right, those belong to the Texas, okay? The Texas companies. And the same, this is the no more than one investment can be made in foreign companies. So you look for all the foreign companies, right? Investment. So you can see here, thus, two are foreign. So you either choose the British Petrol or Dutch Shell. In other words, B plus D should be less than equal to 1 because those two belong to the foreign company. Okay? And then the next constraint is exactly one of the two California companies must be included. So it's exactly one of the two California. So that's why here we have equal to 1, right? And look at the table, the California one is the last two, means S plus C should be equal to 1 because it requires exactly one of them. And then the next one, so you should pay attention, okay? Says if British Petrol stock is included in the portfolio, then the Texas oil stock must also be included. So we have this B less than equal to T constraint. So if you use T less than B, will that be correct?
At least equal to.
So T less than equal to B? Is that correct?
No.
Why? So why do we need B less than equal to T instead of T less than equal to B? What is the difference? So you have to pay attention to those statements. Actually, in your exam, like we have like the hired agent and the needed agent. So those two keywords are different. Hired means the people you hired. Needed typically are specified by the problem. So here says the British Petrol stock is, if the British Petrol stock is included, then the Texas oil stock must also be included. So, okay, let's say this. If T less than B, if T equal to 0, B equal to 1, that satisfies this constraint, right? But apparently, that's what not this constraint, the statement is saying. It's saying if the British is included in the portfolio, then the trans-Tex oils must also be included. However, can you do that? T is included, but B is not included? Means the Tex oil investment is included, but the British petrol stock is not included. Will that be okay? That is okay. So what is it saying? If B equal to 1, then T must equal to 1. If B equal to 0, T could be either 0 or 1. Okay? That's why you have this B less than T. So in other words, if B equal to 1, T must be equal to 1. So T greater than B. Okay? Is this clear? Yes? Yes? Okay. So now you have another additional constraint. So above this, the same as the linear programming model, here I'm adding all this decision variables is equal to 0 or 1. So not only integers, the values have to be either 0 or 1. So that's why we call this as binary variables, okay? Are we good? Yes? So let's see how we use Excel to solve it. Here, the columns, you have this 7 decision variables, and they are either equal to 1 or 0. And this is the expected annual return. And that is the objective, you have to maximize this, the total return of investment. And you have those constraints. This is for investment limit. So you have the cost coefficient for each investment. And this corresponds to the model. Correspond to the model. So here, so for the foreign companies, this is for the here. Foreign companies, it's just the 2, right? B plus D. So that's why corresponding to the column B, you have the coefficient of 1. Corresponding to D, you have a coefficient of 1. And for this, here, this is actually corresponding to the last one, the B less than T. So here, the coefficient corresponding to B is 1. But here, what the formula you would choose? The right-hand side. Here. For the for the British Energy Texas company. So what I'm saying here, would you put just a number or a variable cell address? Right, because it's B less than T, so you need to look for this T, right? So should it be this address, right? So that's why it should be equal to B5. So what is the alternative way to put that constraint in the Excel? You can put the right-hand side as equal to 0. So here we have this constraint, right? B less than T. So you can reformulate it as B minus T equal to 0, right? Same. And then here you can add -1 here, but then you have to change the right-hand side equal to 0, okay? So either way is fine. Are we good? Yes? Okay. And the others is for the Texas companies. You have 3. The model here. T plus H plus L less than 1. So you have this, right? T plus H plus L. And so this has to be greater than 2, right? That's what we have. And this is for California companies. Have to be exactly equal to 1, okay? And then when you solve it, you have to put this additional constraint, saying this, all the decision variables have to be binary. So here you choose this being, then the binary would appear automatically, okay? So basically in the middle box, you choose the being, and then the binary will appear on this right side box automatically. And the others are the same as the linear programming model, and solve it, you will get the solution, okay? So before I go on, I would like you to spend some time to do the exercise for this example. So I already uploaded the template on Canvas. So we can spend some time on this first. Are we good? Yes. So you know the difference, right? How to solve the integer programming model. So you either choose those decision variables as integer or the binary variables and solve just as a linear programming model. And you are able to get the optimal solution. Okay? So now let's look at another application. We call it the mixed integer models. So this is typically used for the fixed charge problem, and the binary variables for fixed cost, and the linear or integer variables for the variable cost. So let's look at this example. So what do we need to decide? First of all, what is the problem for the current setup? For the existing facilities, can they meet the requirements? No, right? So here, see, the monthly demand is 46,000. And for the existing plans, the monthly plan is 35,000. So you do not have enough supply. Therefore, what? You want the right to open another plant. You have two choices. One is in Seattle. The other is in the Birmingham. So what is the difference between those two plans, the two candidates? The cost, right? So if you open the plant, first of all, the fixed cost, monthly fixed cost of operating a facility in Seattle is $400,000, and in the Birmingham would be this much, right? $325,000. So the fixed cost is different. What else is different? Because the locations is different, then the transportation cost from this new facility to the client, the warehouses, places, transportation cost is different as well. So we needed to say which one is a better choice, right? So here is our problem. We needed to decide which side we should open a new factory, and the currently either factory can supply the demand to each of this warehouse. Now I want to okay, you also have the production cost for each plant. They are also different. So what happened? Okay, here. So my laser pointer today is weird. Guess the battery again. So the total supply of this existing plants are 35,000, and the demand is 46,000. So you are thinking to open a new facility, and the new facility it should supply 11,000 units. And in the graph, you can see that either new plant, potential plant, can supply the demand for each of the warehouse. So this is the transportation cost from each plant to each warehouse. Okay. So we have two kinds of decision variables. One is the binary decision variable. So we use y as to denote the whether the Seattle is selected for the new plant. If it is selected, that equal to 1, otherwise equal to 0. The same for the YB. So YB is the indicator variable for the Birmingham. So if Birmingham is selected for the new plant, this decision variable equal to 1. Otherwise, it's equal to 0. And then we have the regular decision variables, that's Xij. So that is number of units shipped from the plant I to warehouse J. So I is one of the plants, so should be the C, K, P, or this existing facility, so Cincinnati, Kansas City, and Pittsburgh, and then S or B, so Seattle or Birmingham. And J is your destination node, so this is the either Detroit, Houston, New York, or LA. So your objective is to minimize cost, and this portion are the same, right? This is just the number of units and then time the shipping cost. So this is the new one. So here, YS means, okay, if the YS and the YB are the binary variable, sometimes we call it integrator variable. So integrating if the city is selected for a new plant or not. So YS, if YS is equal to 1, then you have to incur this fixed cost. So this is the fixed operating cost. Okay? Then we have the regular constraints, right? So for each supply node, you have the, what is this again? 0 is the, what is 0? Inflow, right? So let's look at this graph. So inflow is equal to 0, right? 6090. And what is outflow? All this, right? XCD, CH, CN, and CL, right? So that's what we have minus the total of this outflow. Where did I get this? Negative 15,000. Yeah, that's the supply from that plant. So that is negative 15,000, okay? So we do the same for this Kansas City and Pittsburgh, okay? Then you have to be very careful about this new facility, the Seattle and the Birmingham. So in the Seattle supply, the left side is the same. So you have the inflow is 0, and outflow is from SD, SH, SN, and SL. However, for this right-hand side, you know if you open a plant, a new plant in Seattle, then Seattle plant has to supply 11,000 units. But you have to multiply YS. Why is that? Because if you do not open that plant, means YS equal to 0, then you shouldn't have any outflow in the left-hand side. Okay? Only if YS equal to 1, you would have this outflow. Moreover, the total outflow should be equal to 11,000. So that's what this means. But what we are saying here for the Birmingham supply, why do we have this? Similar, right? If YB equal to 0, that means what? So if this equal to 0, Birmingham is not selected for the new plant. Therefore, the outflow should be equal to 0. However, if YB equal to 1, means this Birmingham facility have to supply 11,000 units. So the total outflow, you add them up, the total one should be equal to 11,000. Makes sense, right? Okay, then let's look at the demand nodes. So that's for Detroit, Houston, New York, LA. So you can see here, you used to only have from the CD, KD, and PD, right? You only have this 3. But now, you're not sure yet if Seattle will be supplying or the plant, the Seattle plant or the Birmingham plant. So you have to add both XSD and XBD, okay? Both. But at the end, do you think will both of them have a positive value, SD and BD? Why not?
We just choose one for.
Right, because we just choose one new facility. This two, the constraints above, will make sure only one of them will be equal to 0. And one of them will be positive. The other one will be equal to 0. The same for do the Houston, New York, and the LA. So all these demands have to be satisfied. Okay? So you can see here, if if the Seattle is selected as the site for the new plant, then actually this one will be gone. Means YB equal to 0, right? And all this will be equal to 0. So this one at the end will be ignored. This will be ignored. And similarly, if YB equal to 1, then, oh, no. Cannot work again. Okay. So this two will be ignored, right? Because YS equal to 0, okay? And why do we need this constraint, YS plus YB equal to 1? Because, yeah, only one site could be selected. So you must add this YS plus YB equal to 1. Okay? Are we good? Yes? Then let's take 5 minutes break. Okay, then we will continue. Okay, so any questions about the formulation? Are we good about having two different kinds of decision variables? So what are they? What are the two kinds? Regular decision variable, right. So the binary variable is the YS, YB either equal to 1 or 0. And the regular variables, that's the number of units from a plant to a warehouse, right? And then after we formulated the problem as this we call the mixed integer programming model, we can use Excel to solve it. So the only thing you need to pay attention is here when you implement those constraints, the right-hand side, you have those decision variables. So let's look at the spreadsheet. So again, we will use the table. So this is from all the plants to the warehouses. And all the cells highlighted in yellow are your decision variables. Moreover, you have this too. What variable do we call this decision variable? Binary variables. So this is to indicate whether the new plant is in the Birmingham or Seattle. And then here, this table is the unit transportation cost from each city, from each plant to the warehouse. So this is given by the problem. And then so what is your objective? Your objective is to what? Minimize two costs. You have to first calculate the shipping cost. Since we have all this unit shipping cost, you know you can use the sum product function, right? Of this table and this table. So this is the total shipping cost. And the next one is the fixed cost. So fixed cost is here from this small table, the integer variable. So use this two yellow cells for this array and this array. So this is your fixed cost. Then add them up. This is your total cost, okay? So the cell in green is your objective value, okay? And all the others are very similar to the transportation network model. So you are calculating this flow into Detroit. So from this B5 to B9. And here the flow out for this Cincinnati, that is from B5 to E5. You add them up, okay? So all this are the same flow in, flow out. Then let's look at this flow balance equation. So you have a flow balance equation for each location. So it means for each plant and for each house. So here this is regular, right? So basically for Cincinnati, Kansas City, Pittsburgh, that's just the minus the supply of each plant. However, for this Birmingham and Seattle, you have to be very careful. The right-hand side, you have this negative 11,000. So again, where did the 11,000 come from?
Birmingham,
That was the difference between what the current suppliers made and what the demand was.
Exactly, very good. So that's the difference between the current demand and the supply. Because the current supply is not enough. You want the new facility to supply this differential, right? Supply. So here, have the 11,000. But you need to time what is B31? Why we need to time B21? Here. So for the Birmingham flow balance equation, the right-hand side, why we just put the minus 11,000? Why do we need negative 11,000 times B21? B21 is this integer variable. Right, because you do not know whether this facility is chosen or not. If it's not chosen, your supply is 0. So that's why you need to time this integer decision variable. Okay, don't forget that. Otherwise, you will get the wrong solution. And the Detroit, Houston, New York, and the LA, they are also similar to the network model. Then we have additional constraint. That is the total number of new plants. That's B21 plus C21. So this two decision variable, adding them up should be equal to 1, since you only want to have one new site. Okay? Are we good? Yes? Yes? Okay. So then, let's look at the solver. So we know the objective is the cell in yellow. However, the variables you need to choose this is one table, and then this two, okay? B21 to C21. So you use comma to separate. So first choose the table, then comma, choose this two, okay? Cells. And then also in the constraints, you must add this P21 to C21, means those two indicator variables equal to binary. Don't forget that, okay? You have to add this constraint. So if you look at the solution, which location is selected? Right, that is the Birmingham, right? The Birmingham is not, Birmingham is selected, that is equal to 1, and Seattle is equal to 0, the indicator variable. So if you look at the flow in and the flow out, look at the flow out from Seattle, that's equal to 0. And out the Birmingham, it's equal to 11,000. That's the difference, okay? So at the end, you will see the flow balance equation in Seattle also, the left-hand side equal to 0, right-hand side also equal to 0, okay? Are we good? Yes? So I will give you a couple minutes to implement the model in your Excel. Again, use the template that I uploaded on Canvas. So, can you open the spreadsheet? So, if you look at here, the Cincinnati 73, look at the table, the transportation table, the slides. Okay, this here. So you have 25, right? This is 25, for example, to Detroit. Cincinnati to Detroit is $25, right? So look at the table. So actually, this is 73. In other words, this unit cost already add. Yeah, I will explain. Yeah, that's got up. I forgot.
Okay.
So I will explain the whole class.
Yeah.
Okay. Are we good? Yes. So I want to ask you a question. Here, let me see here. Which cost did you put in the cell, the Cincinnati to Detroit? Say that again.
Do we need to put the shipping cost or the arrival cost? I mean,
The production cost. Right, right. So you actually adding, so if you look at the table, the shipping cost here, actually put it here, I guess. Where is it? Here. This is $25, $55, $40, $60, right? This is the shipping cost from Cincinnati to Detroit, Cincinnati to Houston, Cincinnati to New York, Cincinnati to LA. But then here, this is the production cost, right? The Cincinnati is $48. So you are adding $48 for the first row. So 48 plus 25, 48 plus 55. In other words, in this cost, including the shipping and the production cost. Do you know what I'm saying? So means if I give the 1 unit to Detroit in Cincinnati, I needed to first produce that 1 unit, then deliver the 1 unit to the Detroit. That's why I'm adding that to cost. Okay. Is this clear? Yeah. Thank you for your asking. Yeah, I forgot to explain this. Okay. So did everybody get the solution? We're good? Okay, so you know how to solve the integer programming model. I already uploaded the homework 3. It will be due on this Friday, and you should be able to do the first 5 questions now. So I would recommend you start to do now. Don't wait the last day, okay? So the linear programming sensitivity analysis, you cannot do it yet, but the first 5 questions, you should be able to do it. Okay? So I want to also talk about the linear programming a little bit. Since the next class, we will be reviewing the exam. And also, I needed to talk more about the linear programming sensitivity analysis. So I want to furnish some of them today. So for the sensitivity analysis, we want to see what will happen if the objective function coefficient changes or right-hand side changes. So when we say the right-hand side changes, what does that mean in practice? The right-hand side of the constraint.
Your demand is, you can satisfy more of your demand.
So based on the problem. So here we are saying like for the linear programming, typically like for the resources, the right-hand side is the limited resources, right? So for example, for the wiring hours, available labor hours. So if for example, I hire one more employee, of course, the available hours will be more, but you want to say whether it's worthwhile for you to hire another employee. So you want to say, okay, whether the change of the profit is worthwhile, right? So that's why we are saying, okay, what happened when the right-hand side changes? And if the objective function coefficient changes, means like profit margin changes. So if I want to increase my selling price for a product, is that worthwhile? Okay. So recall this furniture example. So we have this tables, number of chairs to be produced, and we have the carpentry hours, painting hours, right? Limitation. And we know how to solve it. So we used this model, and I mean, here we have the maximum chairs allowed, constraint, maximum tables allowed, also those limitations as well. So we use the graphical method. We can draw all these constrained lines and get the optimal corner solution is on 4. So this is an example we used in the linear programming session. But now we want to say, okay, when my objective function coefficient changes, or right-hand side value of a constraint, the constraint coefficient changes, what will happen? But we only will look at these 2, okay, cases. So here, the objective function coefficient, this is the profit margin, right, on the table or on the chair. If I change the profit contribution, means the profit margin, for the table, change it from 7 to 8, or 6, or 11, or 3. What will change? Do we think so if I change this 75C to 85C because my profit margin increases, do you think the optimal solution will change? If I change? Yes, no. So think about the change in the graph, the profit line, right? If you change the coefficient, you change what? The slope, right? So do you think the optimal solution, the corner point will change?
Yes.
Maybe, right? So could change, okay? Depends, right? How about the feasible region will change?
Let's say, depends on constraints.
Only change the objective coefficient. So you will not touch the constraints. Therefore, the feasible region will stay the same, okay? But the slope of the profit line will change. And if the slope changes too much, of course, the optimal solution will change. So look at it here. If I change just from 7 to 8, the profit margin for the table, does it change the optimal solution? No. However, look at here. I changed the profit margin for the table from 7 to 11 or to the 3. Then the optimal solution actually changes because the slope changes drastically, right? So the optimal solution changes. But the feasible region always stay the same. Okay? So in summary, if you change the objective function coefficient, two possible things can happen. The current optimal corner point remains optimal, but still, even your current optimal solution remains the same, will the objective value change? So in the previous case, this, you change it from 7 to 8 for the profit margin on the table. So from the graph, you know the optimal solution is not a change, still optimal. But will the objective value change or not?
Change, yes.
Must change, right? Because you have the same number of t and c, but here you have 8 times t. So the objective value must change, okay? And the other case is the original optimal solution is no longer optimal. Okay, then the value of decision variable would change. How about the right-hand side of the constraint changes? Means the resource, the limited resource, right? The value of the limited resource changes. If it is a non-binding constraint, do we think the feasible region will change? Do you remember what is the definition of non-binding constraint? What is binding constraint? Binding.
Feasible.
No, binding constraints. What does binding constraints mean? So in the solution, the optimal solution, the left-hand side of the constraint and the right-hand side of the constraint, they are the same or have some difference for the binding constraint? They are the same. Means you are using up the resource, right? In the graph, means all those constraints, like here, right? For those lines characterizing the feasible region, those are binding constraint. But for non-binding constraint, if you substitute the optimal solution to the constraints, the left-hand side and the right side, they are the same or not the same? Not the same, because you haven't used the resources. So those constraints are non-binding. Okay? So, okay, in here we are seeing the binding constraint. If you change the, must change a feasible region, right? For the binding constraint. Since here, look at here, this is the binding constraint, right? So if you move, so let's say, okay, here, I have an example. The painting time from 1,000 to the 1,300, from 1,000 to the 900. So let's look at if I increase the painting hours to 1,000, what will happen? So this increase in resources could allow us to increase the production and the profit. So look at the graph, okay? This is the original graph, the feasible region. And you know this is the binding constraint, and you increase the number of available painting hours, and your feasible region change it to this. Because you move this line up. So you have bigger feasible region, right? And this red one is the extra feasible region because you increase the number of painting hours. Okay? So your new solution actually will be here. So the constraint line shifts, which could change the feasible region, but the slope of constraint line changes or not? No, because you're only changing the right-hand side. And the corner point location could change, okay? So here, this is changes. You saw that, right? So this is corner point, but now you have this corner point, right? And also this one too. The optimal solution also can change. So let's look at it here. This is the original painting time consumed with 1,000 hours, and 4 is the optimal solution. And now you increase the painting time to 1,300 hours, and your new solution is new optimal solution is the 4A. So that's this one now, okay? 4A becomes your new optimal solution, and your profit become $4,820. Means you increase the available painting hours, your profit changes. So this is the new optimal solution. So T is 560, C is equal to 180. So you want to say, okay, then how much is this painting hour worth? So here you have this profit. Okay, that's like the average painting time dollar. So here you have the new profit value minus the original one divided by the increase of the painting time. That's 300 hours, right? So that is $2.6 per hour. So in other words, if the cost of having one additional painting hour is less than $2.6, it's worthwhile. But if the employee is too expensive and providing the one additional hour, you need to cost more than 2.6 hours, then forget about it, right? Forget it. You don't want to have more painting hours. Does that make sense? Yes? Also, okay, so this is how we calculate it. Okay, so this is the profit increase, and that's the additional hour increase. So also we are saying if you lose one hour, then you will decrease the profit by 2.60. But how about if I decrease my painting hours to 900 hours? Do you think your profit will decrease? Must, right? But you want to know how much I'm losing. So again, I'm finding so this is the loss of the feasible region, and then you are finding the new optimal solution, okay? We will have the new optimal solution is for B here, and this is the new optimal profit, $3,780. So you want to calculate per hour, like how much is the profit decreasing. Find out should be the same, 2.6, okay? In other words, if I'm losing an employee hour, my profit will decrease by $2.6. Okay? Is this clear? Yes? So actually, do you think, for example, I increase the painting hours to 2,000. Do you think the average value per hour will stay the same? So for now, like I'm doing this with decreasing 100 hours and increasing by 3,000 hours, my the average dollar per hour is the same. My question is that true for any range of the increase or decrease? No. So I will explain more on Thursday. So actually, in the solver, the Excel solver, you could choose the sensitivity analysis, all right? So it will give you an information within which range this value, later on we will learn this is a shadow price, the value will stay the same. But if beyond this range, then this value will change. You have to resolve the problem. Okay? Questions? No? Then I will see you on Thursday.